All right. Thank you for the introduction. It's great to be up here, and it's fantastic to be involved in this new space. I'm not used to this kind of a view here, so forgive me if I get distracted during the talk. I'm going to be talking a bit about multimodal AI for aligned robot systems and talking about how we can take advantage of sort of multiple modalities in order to manage a problem that's near and dear to my heart, which is aligning AI systems and setting goals for AI systems. So first, just a bit of background about me. I run the algorithmic alignment group here, so I get to work with these lovely students on a regular basis, and it's a real joy. Today, what we're going to be talking about is really kind of sort of two parts. The first part is we're going to be talking about what is reward design in the context of AI systems, and in particular, why is it challenging? And next, as you might expect, we're going to talk about how multimodal AI can help us solve this problem. And in particular, there are two methods that I'm pretty excited about here. One of them is the use of vision language models in order to make reward design easier. So we can make it so that rather than kind of typing in numbers and tweaking weights, you're specifying rewards in language in a way that's naturally interpreted by AI systems, as long as you can render it into a reasonably realistic kind of image. And the second approach is looking at integrating language and preference learning into robot control. So how can we take language as a modality and integrate that into the control of AI systems through hierarchical representations and similar kinds of approaches? So first, kind of robot control 101, AI systems. The simple story for how we control robots is you start off, you have a robot, and then the first thing you do is you think about that robot existing in some state space. So in this case, maybe there's a robot and there are these objects around that it can manipulate, and then you have a set of actions that the robot could take. So maybe it's able to grasp objects, or it's able to move and pick some up. So if you grasp, you get to a final state where you're picking up maybe this blue object, or you might move to go pick up this orange object. And this gives you kind of a layout of different options and action sequences the robot can execute in the world and the consequences of those actions. And then the last thing you have to do is tell it which of those action sequences are preferred to which other ones. And we do this through the use of a reward function. So if our goal is we want to pick up the blue ball in this case, we might say that this is a reward of 1, and then we have a reward of 0 everywhere else. And this is summarized in this lovely equation up here, where we want our robot to maximize over a sequence of actions the sum of rewards that we get from some state space. And this formalism here is called a Markov decision process. You see variants of it all over the place. So kind of one example of this in a slightly more realistic setting is if we're trying to control this robot arm, and we've got this person nearby and we've got this vase, we might think of the state being the position of the robot xh, the position of the human xh, the position of the robot xr, and then the position of this vase here on the table. The actions are going to be changes to the robot's control joints, so moving the arm around. And we can think of our reward function as being a weighted combination of distances from the robot to various points that are important in the world. So we might measure the distance from the robot hand to the person's head. People don't like it when your hand's in their face. Similarly, you might look at the distance from the robot to the person's torso, also good to avoid, but maybe less important than the head. Distance to the table, and of course, distance to the vase overall. And then when I went to grad school, kind of something I ended up spending a lot of time doing was this process here of basically tweaking these weights. So along these sliders, we're controlling the magnitude of these weights. How bad is it to be near these different target locations? And as you can see, the robot behavior for the arm is kind of adjusting over time. And you basically continue this iterative design loop until you get the robot to do what you want it to do. And when people talk about reward design, this is really the process that they're involved in. It's kind of like programming, but for robot control with rewards and incentives rather than general purpose code. And so the first thing that this points out, and the first thing I recognized in the course of my PhD, was that this is actually a bit of a fiction of a story, right? This is telling us that the reward function sort of comes down from the heavens and tells us everything it's supposed to do. In practice, this process of iterating over that reward function is a critical piece of how we actually get systems to work. So there's some designer sitting outside of the system that's kind of determining what this reward function is. And what's interesting is that it's not actually just a matter of like, oh, once you get it to work in some settings, it works everywhere. Actually, this process is really, really brittle. So you go to some new situation and the arm sort of sweeps right through the vase. So it's not just that we have to think about the process for specifying these rewards, but we also have to recognize the fact that they might be wrong. And so there's a reward you get, and that's going to be different from the real one. Here's another example of this, which I beat into the ground a little bit at this point, so apologies if you've seen it before. But this is a robot that's kind of supposed to do this boat racing game. And the reward function in this case is a reasonable one, but one that leads to an incorrect behavior. So actually, this is the optimal behavior for the reward function the system got. It just so turns out that the designers of the system assumed that if you gave the robot a goal of maximizing the score in this bottom left, then it would cause it to win this game. And it turns out that these balloons are worth points. So if you spin around in circles forever in the middle of the ring, you end up getting an infinite score because you never finish the level. At some point, things crash out, of course, but, it's effectively infinite from the standpoint of the robot. So this is an example of what I'll call Goodhart's law, and which is very nicely stated as once a measure becomes a target, it ceases to be a good measure. So breaking this down, when we say measure here, this is some way of indicating or specifying what your goal is and determining that in the context of the system. When you set it as a target, this means you actually set it as a goal for the system. So the system's going to optimize in some way in order to try to maximize that measured goal. And what we mean by it ceases to be a good measure is that you might start off with winning and getting a high score is pretty well correlated, but over time, as you optimize against it, at some point you sort of fall off a cliff, and that's how you end up spinning in circles. All right. So a small historical fact, Goodhart never actually said once a measure becomes a target, it ceases to be a good measure. It's attributed to him, but actually if you go back into the history books, it turns out that initially Wikipedia, when I was doing my research, had it dedicated to Marilyn Strathern, who sort of said that this is the case. But you go do your homework, actually it turns out that yes, she did say that, but she attributed it to Hoskin as describing this as Goodhart's law. So if you go back and sort of look through, you can actually find this in some obscure accounting book as the original reference for it. And in case you were worried, Wikipedia is now updated, so science progresses and the body of human knowledge extends onwards. So that's Goodhart's law sort of in general. What are some of examples of kind of more realistic cases of it? Well, one of the classics is a paper that started an entire field in economics called principal agent problems. And this is called On the Folly of Rewarding A While Hoping for B. And kind of the summary of it, if you want to go slightly beyond the title, is numerous examples exist of reward systems that are fouled up in that behaviors which are rewarded are those which the rewarder is trying to discourage. And this makes the point that actually this isn't a property of AI systems, this is really a property of human systems in a whole bunch of cases. So there's the famous example of the Cobra effect, which was a case from colonial India where the British were there and they didn't like that all their horses were being killed by cobras, so they created a bounty on cobra heads. You brought in a cobra's head and they'd give you some fixed amount of money. And this worked out really well up until the point where people realized you could just breed cobras and kill them, and that was actually a lot easier than going out and hunting for these pesky wild cobras. Then, of course, once they found out this was going on, they canceled the bounty. All of these cobras that had been bred now get released out into the wild, so your problem's actually worse than where you started. In a sort of less lighthearted example, there's this paper from Mullinathan and Obermeyer called The Iniquity of Predicting A While Hoping for B. And in this case, what they said is the stated goal was to determine individuals that are in need of specialized intervention programs and which intervention programs are likely to have an impact on the quality of an individual's health. So in this case, they're looking at working at an insurance company trying to figure out how can we intervene early in order to prevent poor health outcomes. And as a proxy for this, they use the predicted healthcare costs, the idea being that if you have a high cost sort of healthcare, that means that you're in a poor sort of health state. You're going to incur more medical costs. And of course, in the same way, your health is still, related to these costs, but there's the specification gap. And the key thing that this paper found was that there's actually a really strong racial bias in how that specification gap manifested. This is because in the United States, because of lots of historical reasons, black people are less likely to get healthcare for the same level of lack of health. So what you're seeing here in this picture is a strong measurement of health, which is the number of chronic conditions someone has. And on the x-axis is how risky the algorithm thinks you are. And this gap between the dotted line And the solid line is basically telling you that the system thinks you are sort of much riskier at a much sort of healthier state if you're white than you are if you're black. If we turn to autonomous driving, we can also see examples of this. So this was a paper from last year that went through and looked at reward functions in the context of reinforcement learning for autonomous driving. And what they found, they developed 8 sanity checks to identify flaws in reward functions, and they tested them out on all of these papers. And what they found is that there's basically near universal flaws. And so here's a really simple kind of case of one of the issues that they found. They relied on this idea of an indifference point for risk. The idea is pretty simple. You have 3 trajectories that your car might go on. One of them, the car drives and at some point crashes. Another, it sort of does the safest possible thing, which is it just stays in the driveway. So that's this tau idle. And then at the very last, you've got the car driving safely through to its destination. So that's kind of getting where you want to go. And what they can look for is, what is the probability P where the reward for staying still is equal to some probability P of crashing, and then a probability 1 minus P of driving safely to your destination. And this tells you what's your risk tolerance as you're driving. At what point are you willing to accept the chance of a risky trip in order to get you out of your driveway? And what's nice about this metric is that you can compare it to a probability of collision per mile, or kilometer in this case. And there are standard stats for this that we measure across humans in order to get a sense of sort of how safe people are. So here are some kind of baseline levels. You know, the safest, we've got 50 to 60-year-old adults, and sort of at the like kind of one order of magnitude below that, you've got 16 to 17-year-olds. So those are kind of the most dangerous people that are legally allowed to drive in the US. And you've got drunk teenagers kind of an order of magnitude and a half down below that. Now, where do the reward functions that they tested show up on this plot? Well, they're all the way over here. So driving about, in one case, about 100 meters before an expected crash. In the other case, about 1 kilometer before an expected crash. And this is actually a rosy picture because most of the papers that they looked at failed a basic sanity check and that they actually preferred crashing to staying still. So there's no probability that actually gets to this equivalent measure. So they summarized this nicely, but I'm going to skip ahead in the interest of time here. You can also see this in the context of recommendation systems where this misaligned reward functions related to engagement lead to poor results in terms of recommending things overall. And last, I'll sort of say kind of why does this occur? Well, in a 2020 paper, we looked at this and we found that you can come up with a pretty simple model of this. And you can find that for the increasing your proxy utility in blue, eventually your true utility rises up, crests, and then falls. And this is that specification gap. And what's interesting is that in our model, this is true for any proxy that you might select. So anyway, as long as you are missing some aspect of the true reward function, you're going to end up with this property where you eventually split between optimizing your goal and sort of losing reward overall for what you care about. The summary of this was that this incentive brittleness, the ability to separate your true goal from your proxy, relates to 2 key properties. So if I had lost you at some point there along the way, these are the things to remember. 1, incomplete value measurement. So measuring some partial representation of your goal rather than the entire aspect of your goal is one of the key things that leads to our results. The other aspect of our result depends on having some shared and limited resources. So as long as the things that you care about have some sort of connection to a resource allocation problem, where you have to choose what you actually spend your money and time and effort on, then you'll end up with this split between rewards and this over-optimization property. Now, if incentives are brittle, provably so in a whole bunch of settings, these are pretty general conditions that you might run into. Why do we see them everywhere? And the answer is that actually optimization works really well until it doesn't, right? This initial phase here where reward is going up is often really valuable. What happens is you have this 2-phase kind of property where initially you're actually paying attention to the things that you're measuring much more so, and you're kind of reallocating resources between the things that you've taken time to measure. The problem is at some point you hit kind of the Pareto frontier on the things that you've measured. And now there's only one goal for the system, which is to take resources from things you're not measuring and reallocate them to things that you are measuring. So you kind of go through these two phases where in phase one, you're reallocating resources. And in phase two, you're extracting resources. And notice that this is about optimization systems, not just AI systems. So this plot and this picture could very well apply to climate change and developed economies and capitalism, as well as it applies to AI systems and AI agents and things like that. All right, so that's my little preamble here to get us started. The moral of the story is with optimization systems, optimization-driven systems, you get what you can measure, and eventually that's going to come at a cost to something that you can't. So now what? What are we going to actually do about this? How do we manage this problem? Well, this is not a new problem. Like I said, this is pervasive. This is all over the place. So what we can do is we can look at how different companies and industries that manage optimization systems actually manage it. And we did this in a paper that looked at the state of the art in recommendation systems across industry. And although they have a kind of misalignment between public good, they're actually relatively good at managing the misalignment between their systems and their overall profit motives and their sort of underlying objectives. And they really have a three-step process where they first kind of look to identify what's a scenario where something's going wrong in their system. So you create a name for some undesired concept or thing that's happening in the world. So in recommenders, this might be identifying that something called clickbait exists and coming up with a category for it. It might be recognizing that there's conspiracy theories that are proliferating on your system, or it could be identifying different types of harassment, something like that. The next step is you operationalize that measurement and metric. So in the case of clickbait, they developed a metric called watch time, which was how much time did you spend on a site before you came back? If you go away and come back immediately, that's an indication that maybe it wasn't a very good link. A lot of these systems now leverage ML classifiers in order to implement this step as well. And then finally, you adjust the system, right? So you identify the problem, you come up with a way to measure the problem, and then you adjust your system accordingly. And in a lot of cases, what it really takes in order to make this process work well and to prevent dysfunction in an optimization system is that you run this loop more and more efficiently. So the faster you can iterate on finding problems, measuring them, and then adjusting your system in response, the better your optimization system will be. So the key implication for AI is that we should be optimizing industrial AI processes to rapidly identify unspecified qualitative harms or problems with them, and then rapidly adjust system behavior accordingly. All right, so returning to our overview, what is reward design? Why is it hard? Well, reward design is the process of specifying goals for a system. And why is it hard? Well, because we're always facing these problems of incomplete measurement of our goals and shared resources. Next, how can multimodal AI help us solve this problem? And the answer that I want to point out to you is related to running that control loop, figuring out what's wrong and then adjusting our systems accordingly, which is that I think multimodal AI can make it much, much easier for us to iterate on and augment the rewards that we specify to systems. And I'll give two examples of how we can go about this. The first is through relying on vision language models in the context of reward design. So this is using models that connect language to image representations in order to specify goals. And then second, I'll talk about integrating language into online preference learning and robot control. So first, this idea for vision language models as zero-shot reinforcement learners is a paper that came out earlier this spring, and it's something that I'm seeing more and more research sort of move towards. So credit to the authors on this. The basic idea is really quite simple. Let's go back to this boat racing example. What was kind of the main reason why this went wrong? Well, they used the wrong reward function. But why did they use the wrong reward function? Well, one of the main reasons they did was because that was an easy reward function to specify. If you're looking at just, you only have access to these images, and you want to specify a goal of win the race, well, designing and building a classifier to determine whether or not you are actually winning the race is a challenging thing, or at least was challenging to do in 2017, I think, when this example kind of popped up. On the other hand, cropping that bottom corner and OCRing it, that's quite easy. So they didn't have a good classifier for winning the race. But what's different now? Well, with new models that can connect vision and language, it's not that much more difficult to define a much better reward function. i.e., you can have a pretty good language-conditioned classifier for winning the race, basically out of the box. What's the tool that this is going to build on top of? Well, it's going to be approaches that are built around things called CLIP and other similar ideas. So CLIP stands for Contrastive Language Image Pre-training, and the early versions of it were released by OpenAI in 2021. That system was trained on 400 million text-image pairs, and it was built using an approach like this. So you take your text, you've got a whole bunch of different captions for images, and you have a whole bunch of images down below. You feed both of them through an encoder to get an embedding of some kind. And then you try to optimize the system so that the dot products between the pairs are higher than dot products between alternatives. Pretty simple idea. Naturally, there's a lot of complexity to actually getting this to work. But with lots of data, that now gives you a way to create a zero-shot classifier, where, let's say you want to classify into a whole bunch of different categories here. You take those categories, you formulate a reasonable prompt of what would be a description of one of those. So in this case, maybe a photo of a plane, or a photo of a car, or a photo of a dog, and you compute the embeddings for each one of those bits of text. Then you can compare those with the image encoding and see which one is sort of highest dot product. And that now gives you a recipe to run classification where you don't have to do any additional training beyond the pre-training layer. So if you want to use this as a reward model, the recipe is actually quite simple. Write down a description of the goal state you want the system to achieve. Use a CLIP model to create a zero-shot classifier for the goal state. And then train a policy with reinforcement learning to maximize that reward signal. And then hopefully maybe you profit. I don't know. We'll see if it works. Some of the details of how you do this is you actually want to use the cosine similarity rather than just a dot product to measure similarity. And it's also helpful to add in a baseline image. So if you get some example of a starting state and project the current state onto the line between your starting encoding and your goal encoding, this helps remove some of the extraneous information that could be encoded in the embeddings. They validated this on some control tasks. So here's a connection between the rewards that you have for cart pull, where your goal is in the middle there with sort of angle 0 radians. You can see the reward matches that relatively well. You can also look at this in the context of mountain car. At first, it actually works with this reward function, but you can see it's quite noisy. You want to have the highest value at the far right. But it turns out that if you actually use a more realistic background, then you get better reward performance in this case. I think because it sort of looks more like a car and a mountain, and it does a better job of grounding that out. This is a kind of an interesting caveat when it comes to applying these ideas. And then they used this in order to do some aspects of humanoid control. So here are some examples of success cases where they used the prompts down at the bottom in order to create reward functions that they then applied reinforcement learning in order to control the systems with. As you can see, these are some non-trivial RL tasks that they're getting a very good, relatively good control out of with pretty little reward engineering. I expect they iterated on this to some extent, but those prompts at the bottom are not particularly complicated. Of course, it's not a total story of success, so they had some examples of failures. For some reason, they had trouble getting the humanoid robot to stand with its hands on its hips. Also, kind of crossing its arms seems to have been a challenge, as well as standing on one leg for some reason. So there's clearly lots of room for improvement in this. I wouldn't describe this area as finished, but I see this as a really interesting direction to explore further, where we can take advantage of these new modalities in order to control systems and make it easier to specify goals and iterate on those goals overall. So that's kind of one approach and way that multimodal AI systems can help us with reward engineering and alignment for systems. The other approach that I'm excited about is integrating language directly into robot control. So this is building on some work that I did in 2021 with Michael McDonald on guided imitation of task and motion planning. And the basic idea behind this is that if you just do pure RL, some of the challenges with that humanoid control was related to it just being difficult to get RL systems to optimize effectively. And so you can see what you'd like it to do here is to actually pick up that object using its gripper and move it to the target. And it's going to succeed, but it's not actually using the gripper in the way you want. On the other hand, we've got lots of planning systems that can do this really, really effectively. And in particular, this is drawing on hierarchical control systems, where we're planning out sequences of grasp, move, pick, place, things like that. So this type of an approach goes back and forth between using a task planner to come up with a candidate high-level action sequence and then using a motion planner in order to ground that out into individual steps. And what we did in this work is we trained a policy to imitate both of those processes. So we both learned how to predict for every state a policy that would tell us which high-level action to take. And then for each one of those actions, we learned a separate control policy that we could use to implement it. And then we finally picked those selected from those control policies to actually control the robot system. We're able to imitate this without too much difficulty by collecting data from this system and training it to capture both of those. And we had some pretty nice results where we're able to do like robot control in a pick place setting, as well as this kind of image-based control setting with all of these different tasks, all with a single network across these different goals. Now, the thing to notice about this as an overall system is that because we're breaking things down into these high-level actions and steps, there's no reason why we can't have those high-level actions also integrate dialogue-based preference learning. So in addition to saying pick or place or move over there, you can say, ask some questions, learn some more information about your goal, talk to the person about what you'd like them to accomplish. So the basic recipe is that we're going to utilize beliefs-based planning to incorporate uncertainty over goals for the robot, and then we're going to integrate dialogue actions in order to reduce uncertainty over the goal. And this is building on some prior work that can do task and motion planning in belief space. So this basically looks like the same problem as finding an object where you don't know where it is, but instead it's figuring out which object you want to find. There are some ideas around how you represent these types of beliefs for planning systems. And the overall changes to the system are pretty simple, which is during the planning phase, you incorporate a belief-based tracker into the actual task and motion planning system. And then during execution, all you have to do is integrate a recurrent or attentional architecture in order to handle the history dependence of the policy. So with this architecture, there's no reason that we can't use open-ended dialogue as a high-level action to reduce uncertainty. So we'll be looking at settings where the person knows what goal that they want, and the robot is going to be able to take their uncertainty about the goal and resolve that through language actions. And I think this provides a much more efficient way for us to have systems that learn and interact with us in the ways that we want. So in summary, what is reward design? Why is it hard? Well, incomplete measurement and shared resources. How can multimodal AI help? By making it easy to iterate on and augment rewards through vision language models and reward design, as well as integrating language and preference learning into robot control. And with that, I'll stop here and I'll take questions.